Welcome everybody. I'd like to try to answer a question that asks, what conditions are necessary for rotational equilibrium? So we need to back up a little bit and define what equilibrium means. Equilibrium is a state of balance, and balanced systems do not accelerate. This is the familiar form of Newton's second law for linear motion or translational motion. If the sum of the forces in the horizontal direction is zero, you have no horizontal acceleration. And likewise, if the sum of the forces in the vertical direction are zero, you have no vertical acceleration. It's the same equation, it just takes on a rotational form for rotational equilibrium. If the sum of the torques about a pivot are zero, you get no angular acceleration. That is, it doesn't start to spin or slow down. In order for the net torque to be zero, what you have to do is have all the clockwise torques canceled out by all the counterclockwise torques. So what affects a torque? Well, force affects a torque. How big the lever arm is, and the orientation of the lever arm and the applied force. So what are these three variables that affect torque? Well, obviously the harder you push, the greater the torque. So if you apply 10 newtons, you will get twice the torque than if you apply 5 newtons. Where the force is applied also will change how much torque there is. The closer to the pivot, the smaller the torque. The further away from the pivot, the greater the torque. The orientation of the force and the lever arm also affect the size of the torque. So if the force is applied perpendicular to the lever arm, maximum torque. If the force is applied parallel to the lever arm, that is passing through the center of gravity, zero torque. And if the force is in between, well then a portion of the force, that is the cross product of the force and the lever arm, is what you want to calculate. So traditionally, if the lever arm is horizontal and the force is applied like this into the fourth quadrant, this theta describes the orientation. So a portion of the force is going to be perpendicular. And for this example, it's the vertical, the negative y portion. So hypotenuse multiplied by sine of theta will tell you the opposite leg of this triangle. Let's do a simple physical example of this. This textbook center of gravity is right about there, and we're going to apply a force through the center of gravity. Notice, no lever arm, no rotational motion. That is, even though it accelerates, there's no rotational acceleration. And so this is called rotational equilibrium. Even though we're translating, there's no spinning. Now let's shift the lever arm down to here. So if we apply a force at the bottom of the book, there is a lever arm, and we do get some rotational acceleration. What if we were to shift the center of gravity? What if we add mass to the top of this book and apply a force in the same spot? Well, now there is a distance in between the center of gravity and the applied force. So we do get rotation. The center of gravity has now been moved up here. So in order to have no torque, we have to apply a force through the center of gravity. Hopefully that's helpful to understanding what situation is necessary to have no angular acceleration. That is rotational equilibrium. Thanks a lot. I'll see you in the next video.